Chemical bonding is a super complex phenomenon, and anytime in science when things are complicated, models are used to simplify things. One type of model that is used to help explain and represent covalent bonding is Lewis theory. The Lewis theory is the simplest way to represent bonding, but it can still be used to help understand and predict chemical behaviors. The Lewis theory was named after an American chemist, G.N. Lewis, and he used dots and lines and chemical symbols to represent molecules. Now we know molecules don't have lines and dots on them. That's why we call it a model. So the model is called a Lewis structure, and a Lewis structure can really help us predict the shapes and orientations of atoms in molecules. And it can even show us how atoms arrange themselves to form the most stable molecule. So they can help us explain why water is H2O and not H3O. And if we do have something that is H3O, we can look at it and determine how it will react and how it will behave. In this video, you will learn how to draw Lewis structures of molecules, but we will only be drawing simple Lewis structures, so those that contain just single bonds. We will learn how to do multiple bonding and other exceptions later on. So these are the rules for drawing Lewis structures, and it might seem like there are a lot of them, but they go really fast, and eventually you will be able to combine rules and skip over certain things because you feel comfortable with the material. So we're going to start out by drawing the molecule ammonia, which is NH3. The first thing that we need to do is determine the type and number of atoms in the molecule. This is really simple. We have 1 nitrogen and 3 hydrogen atoms. So, like I said, these rules are very simple, but I'm breaking it down into the smallest possible steps because I assume you're learning this for the first time and it's easier that way. The next thing you need to do is determine the total number of valence electrons present in the compound. Now, the reason we care about the valence electrons is because these are the electrons that the atoms bring to the table to share. And that's what we're doing here. We're covalent bonding, so they're sharing electrons. Now, nitrogen has 5 valence electrons, and there's only 1 nitrogen atom. So nitrogen is going to contribute 5 valence electrons to this compound, to this molecule. Hydrogen, since there are 3 of them, will contribute a total of 3 valence electrons, 1 each. So the grand total of the number of valence electrons that are being shared or represented really in this molecule is 8 valence electrons. So this is the total number of all of the outer electrons that can be used for bonding purposes. The next thing we need to do is arrange the atoms to form a skeleton structure for the molecule. Now there are certain rules in that specific rule. If carbon is present, it's the central atom. Otherwise, the least electronegative atom is central, so farthest away from fluorine, not counting the noble gases. Hydrogen is never the central atom, so hydrogen will always go on the outside. Usually, I fill in my hydrogens last, so I fill in the atoms that I know will go in the center or near the center, and then I surround everything with hydrogens. So I have something that looks like this. This is my skeleton structure. N surrounded by 3 hydrogens. Now the next thing you need to do is connect the atoms by electron pair bonds. So these bonds are represented by lines, and each line represents 2 shared electrons. The next step is to add unshared electrons in order to complete octets if needed. So let's look at each atom. Now the whole purpose of bonding is because these atoms don't have full outer shells to begin with. They're just atoms with empty outer shells, just valence electrons. So they have to use their valence electrons to complete their outer shells. Now for most atoms, their outer shell just needs 8 to be complete. Some atoms are exceptions to this. Hydrogen is an example of that. Hydrogen only needs 2 electrons to have a complete outer shell. And our 2 electrons are represented by the bond that is between hydrogen and nitrogen. So all 3 of these hydrogens have a complete outer shell now that they are bonded with nitrogen. The nitrogen needs 8 to have a complete outer shell. And all we have is 2, 4, 6. Each bond represents 2 electrons. So we're missing 2 electrons in this nitrogen atom to complete its outer shell. Well, what do we do in that situation? Well, we just draw electrons in the form of dots on that atom that's missing those electrons to complete its outer shell. So now nitrogen has a complete outer shell, 2, 4, 6, 8. It's a full octet. The last thing we do, and this is going to be very important later, it's not so much important in this specific video, but later on this will become very important. We need to make sure that the number of electrons shown in our structure equals the number that we were given to kind of play around with at the beginning. So this structure can only have 8 valence electrons represented on it. Now if we go back and check, of course, 2, 4, 6, 8, we count 8 valence electrons or 8 electrons represented in this molecule. So this molecule is complete, it's done. You don't need the highlighting on it, but you have nitrogen in the center surrounded by, bonded to 3 hydrogen atoms, and then on the nitrogen there are 2 electrons that aren't participating in bonding. These electrons are non-bonding electrons. Now let's do some practice problems. We are going to start out by drawing water. We have 2 hydrogens with 1 electron each, 1 valence electron each. We have 1 oxygen which has 6 valence electrons, and that gives us a total of 8 valence electrons that we need to represent in this molecule. The next thing we'll do is we'll draw the skeleton structure of the molecule. So we'll put our central atom in the middle, surround it by our hydrogens, and then draw our bonds. And then we need to make sure each atom has a full outer shell. So the hydrogens each have 2. The oxygen needs 8, but it only had 4. So we need to add 2 extra pairs of electrons on it. And that will give us 8 total valence electrons in oxygen and 8 represented in the whole molecule, which is what we want. Now there's a special name for the electrons that are participating in bonding. They are called the bonding electrons. The non-bonding electrons have a specific name, and that is called a lone pair. One pair is 2 electrons, and they're called a lone pair because they don't participate in bonding. Now let's draw CBr4. So we have 1 carbon and 4 bromines. The 1 carbon will bring 4 valence electrons to this molecule to participate in covalent bonding. The bromines will have 7 valence electrons for us to work with. That gives us a total for the molecule of 32 valence electrons that we have to work with when we create this molecule. Now carbon usually goes in the center, almost always goes in the center. So we're going to surround carbon by our 4 bromines in this skeleton structure. Then we need to complete the bonds between the carbon and the bromine, and then we need to make sure we have octets on all of our atoms. In order to do that, we need to add lone pairs to those bromines. So we have to make sure that we have octets on everything and that we've satisfied that initial requirement of 32 valence electrons. Now let's take a look at methanol, which is CH3OH. So why is it represented as CH3OH and not CH4O? I'll get to that in a little bit, but I'm going to start counting out valence electrons here. We have 1 carbon, which gives us 4 valence electrons, 4 hydrogens, which give us 4 total valence electrons for just the hydrogens, and 1 oxygen, which gives us 6 valence electrons. Add those all up and we get 14 valence electrons that we need to represent. Now back to why it's written like this. The reason the 3 hydrogens are written right after the carbon is to show that the 3 hydrogens will be bonded to the carbon, and then that 1 hydrogen will be bonded to the oxygen. So this is our skeleton structure. We need to add the bonds, and then we need to complete all of the octets. So the hydrogens are satisfied, the carbon is satisfied, and now I've added lone pairs to the oxygen to make sure it's surrounded by 8 electrons. Count up all of our electrons. The red, we have 2, 4, 6, 8, 10, 12, 14 valence electrons. Now I drew it like this, but why couldn't we draw it like this? So here's an alternative drawing for that same exact molecule. And what do you do when you get a molecule that can be drawn in different ways? Well, one thing we can do is we can look at bonding preferences. So bonding preferences tell us that carbon and anything in the carbon family will want to have, ideally, not always, but ideally will want to have 4 bonds. Anything in the nitrogen family will ideally want to have 3 bonds. Anything in the oxygen family will want 2 bonds. And anything in the fluorine family or the halogens will want to have 1 bond. Ideally, it doesn't always happen that way, but if we're choosing between 2 different molecules, we want one that's going to follow these preferences over one that won't. So keep that in mind when you're drawing your molecules. Now the last one is easy. It's F2. We're going to end on an easy note here. We have 2 fluorines. Each fluorine will give 7 valence electrons to this molecule to possibly participate in sharing. So we have 14 valence electrons that we need to keep track of. So we draw our skeleton structure, very easy. We represent the electrons using lines and dots. And if we count up, we have a total of 2, 4, 6, 8, 10, 12, 14 electrons. We have 1 pair of bonding electrons in that molecule. That's that line. And we have 1, 2, 3, 4, 5, 6 lone pairs. So a total of 12 non-bonding electrons, but 6 lone pairs in this structure. So let's take a look at fluorine. Now, why is fluorine covalently bonding to itself? But when we throw it with something like sodium, it forms an ionic bond. Now the answer to that lies in electronegativity. Fluorine is the most electronegative atom on the periodic table. That means it really wants electrons. Sodium is not highly electronegative, meaning it wants to give electrons, it wants to give that one valence electron away so it can have a complete outer shell. So when fluorine bonds with sodium, something that has a low electronegativity, it's going to ionically bond. It's going to just take that electron, basically, from sodium. But what happens when it bonds with itself? If they both want electrons, then they're going to have to share. So then they covalently bond, and they form one covalent bond between the 2 of them.